it contains foundational aspect as well as application. For example, in quantum error correction and quantum secret sharing, resource theory, he has phenomenal works. Today's talk is quite interesting, and I'm also very keen to hear about it. You know that entropy and so Shannon theory, for example, is very well known to us, starting from statistical mechanics to sending of information in the network. Information theory and entropy has played key roles. Now, today you will hear that, as you might have seen some of his works previously, that in some entangled states, this entropy becomes negative. Now, that is quite, entropy is, or disorder becoming negative is very counterintuitive. Now, today his talk will deal with this aspect, and particularly he'll point out how the physical laws sort of gives you a natural way of tackling this problem. So let's hear Professor Gour. This stage is yours now. Thank you.
Thank you so much, for the very nice introduction. And it's a pleasure to be here and to tell you a little bit about my recent work. I'll be talking today on the inevitability of knowing less than nothing. And what we mean by that, it's kind of a phrase that came out in recent years since the quantum state merging protocol came out. And it means that conditional entropy can be negative. And I'll discuss it in a minute with a little bit more details. But I will just mention that the title of my talk could be Inevitability of Negative Quantum Conditional Entropy. And this is based on a joint work with Mark Wilde, Sam Branson, and Isabel Gang. And it's also available on the archive. So, let me try. Let me see if I can, for some reason. Oh, okay. So I'll be talking to the main goal of my talk today is to give you an axiomatic formulation for quantum conditional entropy. So this is formulation that will be based on very reasonable axioms. And by doing that, I will prove that every function that satisfies those two axioms that I'm going to tell you about must take negative values for certain entangled quantum states. And this basically justifies why any plausible conditional entropy takes negative values in quantum information. And as I said, it's known as knowing less than nothing. So to start my talk, I would like first to go to entropy. So as I mentioned, I'll be talking today about conditional entropy, but let's start and see what we know about entropy. What is entropy? Intuitively, we know that it's the knowledge gain upon learning the outcome of a random variable, a random experiment, like tossing a dice. Now, this is just an intuition, not a rigorous definition. But we always, before we go and start with the rigorous definition of any quantity, entanglement, entropy, free energy in thermodynamics, anything that in physics, there's always first we have some intuition and then we making this intuition rigorous. So the intuition is that it is some knowledge that we gain once that we learn from the outcome of a random experiment. The example is tossing a die. And if the die is deterministic, suppose like no matter how I toss the dice is not unbiased, it is very biased, and it's always output the same number, then we don't learn anything. In this case, we would say the entropy is 0. But if it is uniformly random, if the dice, meaning that the dice is unbiased, right? So then if there are d possible outcomes for tossing the dice, if it's a dice with 6 faces, there will be log base 2 of 6 bits that we learn by tossing the dice. And also the intuition tells us that if we using successive tosses, then if they are independent, then we expect the entropy to be additive. So this is basically the intuition behind entropy. And in this talk, I will stick to finite random variables throughout this talk, and also when we go to the quantum realm, I'll be talking about infinite dimensions. So an example of an entropy formula is the most well-known one is the Shannon entropy. But also Rayleigh came up with a very nice family of entropies known as the Rayleigh entropies that are defined here. Here, the P of X is the probability distribution associated with the outcome X of the dice. But let's try to think, how can we define entropy from an axiomatic point of view in a way that is kind of convincing? Well, Shannon already introduced an axiomatic approach when he came out with the entropy, and he showed that it's uniquely defined under some axioms. If you drop one of those axioms, you will get the Rayleigh family. But those axioms in those papers, the historical papers, they are not very natural. If you look at them, they are very kind of geared towards getting the formula. It's basically quite mathematical. So our goal here is to come up with axioms that would make sense, that we would expect from any function that I can call an entropy to satisfy. And we will see that we only need two axioms to achieve that task. So let's start. What are the axioms? Entropy is a function of a random variable. And it's basically a function of a probability distribution. So how can I put certain axioms on a probability distribution, on a function on probability distribution? I need to tell you, I need to compare between different probability distributions. And I would like to define some monotonicity property of an entropy function. But what the monotonicity would be, it would be, I would like to define an operation that makes things more noisy, makes things with a higher, that increase the entropy. So what would increase the entropy? Mixing. For example, I can think about a deck of cards and I'm mixing the cards. Mixing the cards make things more random. Mathematically, we can think about mixing as a probability, as a convex combination of permutations. So I don't know which permutation I perform, but there is some prior that I can apply some probability distribution to the, some probability matrix to the probability distribution, to the probability vector here. So PI here is just the sum permutation that you apply to the probability vector. Basically, you relabel, you're just relabeling. You can think about a dice and suppose that you just change the stickers of the dice. You change the stickers and you do it in a random way. Doing it randomly could correspond to the following scenario where you just perform some permutation. You just change the stickers of the dice, but then you don't remember if you actually changed the stickers or didn't change the stickers. So this mathematically will describe it as a convex combination of either I did the permutation or I didn't do the permutation, and that depends. And that could also be with some probability QI. So that's what this means here, mixing the... and mixing operations has this property that they preserve the uniform distribution. That means that uniform distribution is U here, is the distribution that is all the components are equal. It's a probability vector where all the components of these probability vectors are the same, 1 over the dimension. And if the reason that the matrix M preserves the uniform, why is it preserving it? Why it satisfies this? Intuitively, it means the following. If I already have maximum uncertainty, if we have maximum uncertainty, if the dice is completely unbiased, then all the probabilities are the same, then I cannot increase the uncertainty about the dice by applying mixing operation because it's already maximally uncertain. Okay? So this means that this operation here, which is a stochastic map, a convex combination of probability matrices, is a stochastic matrix, and in fact it's a doubly stochastic matrix because it's preserved the uniform. And in fact, it's possible to show that a matrix M is doubly stochastic, meaning the sum of its columns equal 1 and the sum of its rows equal 1, and it's non-negative. And one can show that if this hold, if and only if you can write M as a convex combination of probability matrices. So this is known as Birkhoff theory. Basically, the extreme points of the convex hull of doubly stochastic matrices. Doubly stochastic matrices is a convex set, and it has extreme points, and the extreme points are exactly the permutation. So every convex combination of permutation is doubly stochastic, and every doubly stochastic matrix is convex combination of permutations. Okay. So now we can define with this intuition rigorously, make it rigorously, and say that an uncertainty measure, and I'll say why I'm calling it uncertainty measure and not entropy, because and the intuition of entropy is that it is uncertainty measure, but it's also additive. So we'll get into it in a minute. But what is an uncertainty measure? It's a function on all probability vectors in all dimensions to the real numbers. And we say that it's a measure of uncertainty if mixing operations, what is mixing operation? Doubly stochastic matrix, when it acts on it, can only increase it, because you can only increase your uncertainty about the dice. Because if I change, think about the dice that you change the stickers at random. What means at random? Meaning like you apply the permutation and then you don't remember if you applied it. That not remembering can only increase the uncertainty. Therefore, we require from a measure of uncertainty to satisfy this condition that is known as sure concave. Okay. This is closely related to a notion of majorization, because we say that P majorize Q if and only if when I order the components of P from the biggest to the smallest, then I can take the sum of the K largest components of P, and if they are bigger than the sum of the K largest component of Q, for all K, between 1 and n, for all integer K between 1 and n, this is how I denote. This is the set of 1, 2, 3, 4 up to n. So if this is hold, then we say that P majorize Q. And it can be shown, there is a theorem that can show it, that this holds if and only if Q and P are related by doubly stochastic. And that means if and only if for any measure of uncertainty, the uncertainty of Q is bigger than the uncertainty of P. So if P majorize Q, then P is more certain than Q. So the uncertainty of P is smaller than the uncertainty of Q. It actually goes opposite order, you see. So this is majorization, but it goes the opposite direction. So this is measures of uncertainty. Okay, let's convince ourselves. Where can I get another motivation? Why I expect measure of uncertainty? Because you see, the uniform distribution is the most uncertain. And that's why the uniform distribution always majorizes any vector here, is majorized by any vector. And the deterministic, like if the probability vector 1, 0, 0, majorize any other vector. But sometimes the vectors are not these two cases, like they are not uniform and they are not deterministic. They are somewhere in between, right? So the probability distribution is could be anything. In these cases, this is the condition that determines if P is more uncertain than Q. If P is majorized Q, then it's more certain and Q is more uncertain, okay? So to motivate this, let's look at this from games of chance. And let's think about two dice. So we have the red dice, which I will call it the P dice, and the blue dice, which we can call the Q dice. And suppose you're rolling this dice and you get outcome. Now, which dice you would choose to play the game if the game is that you have to guess what's the outcome of the dice? I'm going to roll the dice, and the game is you have to guess which number it's going to be. If you are allowed to guess one number, you will choose the dice that has the highest probability for you, the best odds to win the game. So it has the highest probability for one of the numbers to occur. But if the player is allowed to provide k guesses, k numbers that will constitute its guess, then the dice that you will choose that has the best odds to win. So think about the game. Let me clarify again, what is the game? A player provides k numbers, and if one of those numbers occur, you win the game. So what's the probability you'll win the game? If you use this dice, this is the probability that you will win the game, because you will always choose the numbers with the highest probability, and the sum of those probabilities will be the total probability that you will win the game. And if you chose the Q dice, that will be the probability. So what you can see in this simple example, that if P is majorized Q, then the red dice has better odds in all K gambling games. Doesn't matter what is K, if P majorized Q, this is always bigger than this, so you always have better odds to win. Therefore, in this case, we can say for certain that Q is more uncertain than P. So that's why measures of uncertainty must be sure concave. This is a typo here for sure. It's not sure concave, it's sure concave, it's the person. Okay. So now let's go back to entropy. So now we can define entropy from an axiomatic point of view. And that is, it's a function that is not zero. It's not constantly zero. We don't want the function to be the constant zero function that all the time is zero. Okay, so the entropy is a function that is not always zero, but it is a measure of uncertainty. That means it's sure concave, but it's also additive. If you take tensor product of two of them, you get the sum. Okay, so this is an entropy function. Now, what are the consequences of these two axioms? And additive, I'll just mention that this is the distinction between just any measure of uncertainty and entropy, because entropy is additive, is an additive quantity. That's what we're assuming, which is a very reasonable assumption from an entropy function. And what are the consequences of the axioms? Number one, that it's non-negative, and it's equal to 0 for degenerate distribution. So you see, it's quite interesting. Just by requiring these two conditions, you already know that it is cannot be negative, and it's possible to show that it must be equal to 0 for degenerate distribution. Degenerate distribution are distribution that has one probability 1 for some of the outcomes of a dice, for example, and 0 for all the remaining outcomes. That's degenerate distribution. Also, one can show that H is maximal for uniform distributions, and the uniform distribution U, and it's of size, I will assume that I'll denote U here by the uniform distribution and of dimension. It's a probability vector of dimension n, that all the components are equal, and it sums to 1. Its component sums to 1, so it's 1 over n. And if we normalize H such that for U2, so the two-dimensional, it's equal to 1, then one can show that in D dimension, the uniform distribution can be shown to be equal to log 2D. But actually, quite remarkable, there is a very beautiful result came out in 2021 that shows that any normalized entropy functions, entropy function satisfies this additional condition of for normalization, must be it must be a convex combination of Rayleigh entropies. Okay, so this is quite nice. It shows that our two axioms that we propose make sense on the one hand, but also they give us all the Rayleigh entropies, and it shows that only convex combination of Rayleigh entropies can be entropy function. There is no other functions that satisfies these two axioms. So these two axioms, the only functions that satisfies them are essentially the Rayleigh entropy and convex combination of those. Okay, let's go now to the quantum world. So what is a quantum entropy? As inspired by the classical case, we're going to take the axiomatic approach. In this case, I will still denote it by UA, but now it means a density matrix. A UA will be the maximally mixed state. So it's the uniform state. And what is a quantum mixing operation? Analogous to the classical case, it preserves, instead of the vector, it preserves the density matrix, the maximally mixed state. So if something is already maximally uncertain, then any operation that increases uncertainty cannot do anything to it, because anything else is not maximally uncertain. So it must preserve it. What are measures of uncertainty in the quantum case? They are functions from the set of all density matrices over all. This is the notation for density matrices acting on a Hilbert space A, and we're looking at the union of all possible Hilbert spaces. And so this is a function from this kind of set to the real numbers. And F is a measure of uncertainty if it does not decrease under the action of a quantum mixing operation. So if I apply a mixing operation, I can only increase the uncertainty. And M here is a quantum channel. A quantum channel CPTP map from A to B, that what it is, it preserves basically the identity matrix or the maximally mixed state. And therefore, it's also known as doubly stochastic channel or sometimes as a unital channel. And just like in the classical case, we require that H is an uncertainty measure and that H is additive. Then we say that it is a quantum entropy. And then you can conclude from it that H is non-negative for all quantum state, and it's equal to 0 only for pure states. And it is maximally it achieves its maximum value for a given dimension on the maximally mixed state, as one would expect. And if we normalize it, it satisfies this condition. Okay, what are the formulas for quantum entropy? We have the von Neumann entropy. We have the Rayleigh entropy as well, defined here. So those are well-known quantities in quantum mechanics, introduced quite some time ago. Now I want to talk about quantum conditional entropy. And before I'm going to give the motivation for conditional entropy, using the same idea, this background. So now I'm start talking about the new material, the new stuff. But I want to emphasize something different when we talk about quantum conditional entropy. We will define quantum conditional entropy as a function of bipartite entangled states. And bipartite entangled states can be entangled, and they are positive semi-definite matrices. So that's what it means, this notation. Its eigenvalues are non-negative. It's positive semi-definite. And it has trace 1. It acts from AB to AB. So AB and B are Hilbert spaces. So it's operated from the tensor product of two Hilbert spaces to itself. Okay. And we will define the conditional entropy as a function on all bipartite density matrices. So this is the set of density matrices that acting on system AB. Sometimes I use AB for a system. Sometimes I think about it as a Hilbert space, because every physical system has a corresponding Hilbert space. And so we're looking at it as density matrices that acting on this tensor product of Hilbert spaces here. And then we're looking at the union of all Hilbert spaces, okay? And what it does, it takes a density matrix to a number. The number that it takes it to, we denote in this way as the conditional entropy of A given B, where it's depend on rho. So this is how we denote this number, okay? So this is a number, what's written here, just a notation for something that I'll call conditional entropy. But we need to define what is conditional entropy. So let's get some intuition from the classical world. In the classical world, we know that conditional entropy refers to the knowledge gained upon learning an outcome of a random variable x, given the value of y has already been observed. Right? So it's conditioned on y. So I have access to y. So it's essentially the uncertainty of A given that I have access to y. Because I have access to y, the uncertainty about x reduces. Now, if x and y are independent, then I would expect no difference between entropy and conditional entropy because they are independent. Having access to y doesn't help me anything doesn't reduce my uncertainty about x. That's why the entropy of x will be equal to the conditional entropy of x given y, because if the x and y are independent, having access to y doesn't help. Now, if they are dependent, then the knowledge of y informs us about x, so it reduces the uncertainty about x. So that's why conditional entropy cannot be greater than the entropy of x. Okay? And also, we expect it to be additive for independent trials. So this is the intuition from the classical world. Going back to some formulas from the classical world, still, is one of them is known as the conditional Shannon entropy, which is the entropy of xy minus the entropy of y. Also can be written mathematically like that in terms of conditional probability here. And we have also another example of conditional entropy is the conditional Rayleigh entropy, which are known to be given in this way. Okay, so now that we have some example, let's go to discuss quantum conditional entropy. Now, I would like to define quantum conditional entropy as a function of bipartite states that behave monotonically under some operations. And those operations, we will call them conditional quantum mixing operations. What does it mean? It's operations that increase the uncertainty. But because it is both quantum and conditional, the intuition is it's a little bit it's a little bit more tricky to define the intuition rigorously. So first of all, before going into the definition of a quantum conditional mixing operations, we first need to recognize which systems has maximal uncertainty. And the systems that has maximal uncertainty looks like that. It's a system that is not correlated. Because it's not correlated, having access to B doesn't help. And its A is in a maximal uncertainty. So the conditional uncertainty, the uncertainty of A, of system A, given B, is maximal here because this is maximally mixed. And here I have an access to system B, and it doesn't help me having access to system B because it's not correlated. So this set of states form, those are states that are maximally, has the maximum conditional uncertainty. So now I can use this to define quantum conditional mixing operation. Because what I can say, if something increases the conditional uncertainty, if I have a quantum channel, I don't know what the quantum channel is, just some quantum channel. Now suppose that what we want, we are being told this quantum channel increase conditional uncertainty. If it's increased conditional uncertainty, it cannot increase more the conditional uncertainty of this, because this already has maximal conditional uncertainty. So what I say is if rho is in K in this set, then acting with the channel on that set, I still remain in the set because this also has to have maximal conditional uncertainty, because this can only increase. So what I want from a quantum conditional mixing operation, the intuition in the definition here, is that conditional mixing operation can only increase the uncertainty of system A. But if system A is already maximally uncertain, then I will stay here. It will not take me away. Maybe it will change this state. Maybe it will be a different state, but it's still, this state would still look like this one, like something like that. It would have this form. But this is not the only condition. You see, this is a very similar condition to what we required earlier, that we said entropy mixing operation preserve the uniform state. But when we talk about conditional uncertainty, there is one more condition that M has to satisfy that is known semi-causal. It's known as M is not A to B semi-causal. So I'll have to discuss now a little bit what this condition means. What is M is A not to be semi-causal? So what is a semi-causal? Let's look at the bipartite channel from AB to AB prime. And what a semi-causal channel has is a property that tells us that this channel here, if I trace out system A at the output, no matter what you put here, you feed into the channel. Suppose you trace out this system. So then I have a channel that takes a system AB to B prime. And let's look at the same channel, but suppose I put here another channel here. And I do the same thing, I trace this out. This channel is called A not to B semi-causal if for any choice of channel here, there is no difference. So this channel doesn't affect this channel here. So you see, this E here, Alice cannot signal Bob, because by changing the channel here, she cannot change the channel. It still remains as if it was identity here. It doesn't matter. If any channel that you put here, the result will be the same, as long as you trace this out. But if you don't trace this out, then this makes a difference. But if you trace this out, then there is no difference. Now, from 2002 already, these channels were studied. In fact, they were introduced in 2001. It was proposed that they all look like that, And then in 2002, it was proven that this conjecture was proven. And the conjecture is that semi-causal channels, channels that has this property, they are if and only if the channel can be written like this. What does it mean? It has a channel here and a channel here. So what you can see, if I put here a channel and I trace this out, then nothing affects this, there is no signaling from here to here to B. You see, so there is no, Alice cannot communicate signal to Bob, right? So that's the idea of a semi-causal channel. Now, why we want, let's go back to the definition before. I said I want M to be A, not to B, because we're talking about the uncertainty of A given access to B. So that means, but it's about the uncertainty of A. So I cannot allow for communication from system A to B, because if I can communicate, then I'll communicate A and remove all uncertainty. So we have to require that the channel that increase the uncertainty of A does not allow for communication from A to B. And this is why we have those two conditions. So one is the condition that preserve this form, and the other that there is no communication from Alice to Bob. Because it's a bipartite channel, this is the difference between entropy and conditional entropy. For entropy, we needed to just define channel on a single system. Here we're acting on bipartite system. So there is also some communication that we need to forbid. Otherwise, if Alice can communicate to Bob, she can remove all uncertainty because Bob have access to Alice's system. Now, I'll just say that in the classical world, if A and B are classical, you can show even more, slightly more, that if you remember this picture here, this is in the quantum world. So it looks like a very similar equation. But in the classical world, this arrow here, this is more like a controlled operation. So let's go back to the classical. It means that upon receiving J, so we're sending the system Y through a classical channel that has an output J and an output Y. We communicate J to Alice. Then based on J, Alice applied doubly stochastic matrix on X. So you see, it makes a lot of sense. Those two conditions are satisfied if and only if in the classical world, the channel M looks like this. It looks like Bob apply a channel, get an outcome, send one of the outcome to Alice. Alice then apply to her system doubly stochastic matrix. This is exactly conditional mixing. Doubly stochastic channel is a mixing. Doubly stochastic matrix is mixing. That's what we discovered when we spoke about entropy. And what we have here is mixing condition on the outcome. So Bob, you can think about it as a measurement. He applies a classical measurement, get an outcome J, send the result to Alice. Alice, based on the J, apply doubly stochastic. That's why it's conditionally doubly stochastic channel. That's what we have here, conditionally doubly stochastic channel. So what we learn is that quantum conditional mixing operations, at least in the classical world, literally look like F and D here is doubly stochastic that depends on the J. It's controlled. You see, like what we have here is really controlled doubly stochastic based on the J. We apply a doubly stochastic matrix on the X. And I'll emphasize here that what we had here was not controlled. It was just a channel that whatever you send here, and E didn't have to be doubly stochastic. But if you have both of these conditions satisfied, then at least in the classical world, you can write it like that. Okay. And I'll say another thing. I want to give now a very strong motivation to these two axioms. So those will be the two axioms of how to define quantum conditional mixing, and they will be used to define conditional uncertainty. But I'll emphasize that we have also an operational interpretation for these two axioms. It's not just axiom, but in the classical world, it really, if I assume these two conditions, assuming A and B are classical, then I can interpret it also using games of chance. The way it's done, one can define, look at two dice, but they are this time correlated. So if one gets the probability of the outcome of X is correlated with what Y, the outcome of Y is. And so if we denote this by PXY, a player can provide K guesses for the value of X after he learns Y. Right? So a player can, we can roll these dice, learn Y. Once you know Y, then you can guess what your odds here to win the game. And this would be the probability, essentially, the winning probability, because an outcome Y occurs with probability, let's say, PY, the marginal of Y here. And if a player is allowed to provide K guesses, we discussed before, this is the probability for it to win if it has if the outcome Y occur here. So this will be the probability to win again. Now I will, because I think I'm a little bit out of time now. Let me see. Yeah, I'm getting there. So let me speed up a little bit, and I'll tell you that similarly, you can extend it a little bit, because this is not the only games of chance that you can do. So there is a more sophisticated game of chance that depends on some matrices that on this channel here that is held by the host. And if you define it, a more sophisticated game, you can calculate its probability to win the game. And what it's possible to show that what I defined earlier, that I can say the following, that if in any games of chance, the probability distribution PXY has better odds to win a game of chance than the probability distribution QXY, then it's possible to show that there exists a conditionally mixing operation relating them. Okay, so this gives a very strong motivation to this definition, because this is an operational meaning. So now these two axioms that I wrote here, I gave them in the classical world a very strong motivation that comes from games of chance. And in fact, it's possible to show that in any conceivable game of chance, if all possible games of chance, any choice of game, T here represents the choice of the game of chance. So in all possible games of chance, if I have better odds to win the game with P than with Q, then they are related by conditionally mixing operation. And as I said, conditionally mixing is conditionally doubly stochastic, like that I discussed earlier. Okay, so let's go. I'm very, very soon coming to, I know I'm a little bit probably, I'll go back to the question after the talk. Let me just finish the main concept here. The main idea of the talk is that now when we talk about the quantum conditional entropy, we define it, it's a measure of conditional uncertainty. This means if you apply any channel that satisfies those two conditions, which conditions? Let me get it, where was it? Those two conditions here. Any channel that satisfies these two conditions is a measure of uncertainty. If it's monotonic under channels like that, then it will be a measure of conditional uncertainty. But if we require also that it's additive, if you take two tensor product of two density matrices, then it sums up. And the moment you assume those two conditions, it's quite remarkable how much structure you get. And what example of conditional quantum conditional entropy are the von Neumann, the Rayleigh quantum conditional entropy. Petz generalize it. That's why it's called Petz-Rayleigh sometimes. And we have these functions. And we also have another one that is very useful, known as the conditional mean entropy, that is defined like that, as this infimum here. And the smaller or equal here, meaning that this matrix minus this matrix is positive semi-definite. That's what this means. And the main theorem of my talk is that all conditional entropy, quantum conditional entropy, all of them. What is a quantum conditional entropy? Satisfies these two conditions. I don't know what this function is, because I only know what it satisfies two conditions. But it's quite remarkable. Those two conditions alone forces us to say, it can be shown that any conditional entropy must be bigger than the minimum, the conditional mean entropy. This gives a motivation why to call it, even the name conditional mean entropy makes sense, because it's really the smallest there is. But what this theorem also tells us is that we have equality when the state rho is maximally entangled. If the state rho is maximally entangled, we must have equality, but this guy is negative on maximally entangled state. So what we see here is that quantum conditional entropy must be negative on the maximally entangled state and must be equal to minus log of the dimension. And why is that? Because it satisfies two axioms, that's all. It satisfies only those two. Additivity, quite reasonable. This is, I hope I gave you enough motivation. There is a very strong motivation for the monotonicity in the classical world. In the quantum, it's a work in progress to extend quantum games of chance. That would be nice, but we don't have quantum games of chance developed. So the motivation, the operational interpretation is not there yet in the quantum world, but we have it in the classical. So you can see that it's a very convincing. And let me see what else we learn from this. From the definition of this, you can show that any entropy function is non-negative if it satisfies something known as the reduction criterion, this thing. And this also tells us that only entangled state can have negative conditional entropy. Because all separable state, let's see why. Because if rho is separable, it can be written as a convex combination of product states. And what you can see, I tensor rho can be written as I tensor this part. But sigma, you see, is always smaller than identity. So each term here is smaller. I can replace, if I put identity, it will still hold that this will be bigger than this. So what we see, because separable state satisfies the reduction criteria, this is known as the reduction criteria, the conditional entropy is non-negative. So I'll maybe summarize that. What are the consequences of our axiom? H is non-negative for all separable unentangled state. It must be negative for some entangled state, like the maximally entangled. On tensor product, all of them reduce to an entropy function. It is maximal for any state of this form. And it's lower bounded by the conditional mean entropy. Now, some open problems that is to characterize the pre-order of conditional mixing operations. I didn't talk about it. It's related to conditional majorization. There are several characterizations that exist for it, but not for the quantum in the quantum world. So this is an open problem. Also, find upper bound on conditional entropy. We didn't find an upper bound. We don't know yet how to find an upper bound. I'll stop here. Thank you.
Yeah, thank you, Professor Gour, for a wonderful talk. I think Professor Usha Devi has a question precisely related to this mixing. Usha, you can open and ask yourself.
Okay, thank you.
Yeah.
So a wonderful lecture, which is very, very useful for those who are learning this. My first one question is, you use the word which is operational and axiomatic. I just wanted, for my curiosity, quantum case, you use the word axiomatic, but in the classical, you use the word operational for conditional mixing. Am I right?
Right. Yes.
Okay. I just wanted that.
Good. Yes, this is a very good point, because in the classical world, you see, because someone can come and say, hey, these axioms here, if I look at these axioms, you can say that, well, the axioms were a little bit, let me get them, those two axioms here. But especially of the mixing, you see monotonicity under conditional mixing. So if I apply this conditional mixing, I increase the entropy, I increase the conditional entropy. But why? Someone may argue, well, why is this axioms here, right? Why do I have, you see, those two axioms that are here? Maybe it could be a different axioms, right? Why we choose those?
Okay.
And for those axioms, I in the class, at least in the classical world, I can show that it must be like it's operational. Because if you're playing games with dice,
right,
you can show that if the theorem was there, that if I always have better odds to win a game with the P dice than with the Q dice, then it's related by that. That's the...
Thank you very much. That's a very... One more question that I have is about the reduction criterion that you kind of correlated with conditional mixing. I just have a question that all these unentangled states have zero conditional, positive conditional entropy, and others entangled have negative, but that's not necessary and sufficient.
Right, right.
So now the question is, have Perez's criterion that is also good for only 2x2 and 2x3?
Yes, the Perez criterion.
So how would you put this conditional mixing with PPT and reduction criteria? That is this kind of operation. Would it be?
Yeah, no. So there is two things. So let's. So first of all, it is true that there are states that are entangled and satisfies the PPT criteria. They have positive partial transpose, but they are entangled. It does not mean that they. So the condition that the conditional entropy is positive if it satisfies the reduction criteria here, but if it does, you have entangled states that also satisfies this reduction criteria. Right, so you have some entangled states that it's still positive. It does not mean that it has to be negative for all entangled states. It's just that so it's only one. Now, your question, you mentioned in 2x2 and 2x3 that the Perez criteria is both necessary and sufficient. But again, it's necessary and sufficient for entanglement, not for positive conditional entropy. Conditional entropy can be still positive even if it's entangled.
Correct. Yes.
Yeah.
So, okay, Dipan, you can open and ask question. Yeah.
Am I audible?
Yeah, you're audible. Yeah.
Okay. Sir, in the entangled bipartite state, if we have some kind of decoherence, then what will be a good measure for the H so that it satisfies the axioms?
What do you mean if we have entangled state and then?
No, if we have decoherence in the
you have coherence.
Decoherence in the bipartite state. Like if you're doing some measurements and that introduces some decoherence in the
So
entanglement.
your measurements, so you increase the conditional uncertainty. If your measurements are, for example, quantum measurements on system B, for sure it's increasing the uncertainty, right? Because after you apply something, the resulting state can only have less. You have less correlation, right? If I apply some operation to system B, I can only reduce my correlation with system A from what I had before, right? I cannot increase the correlation because I only applied operations to B. So in the same way, it will increase the conditional uncertainty.
And is there any formulation in which we can purify this thing so that we don't have any kind of changes caused by the measurement, or maybe that?
Like you mean what function it is invariant?
Yes.
For example, local isometries, it is invariant. So if you apply local isometry on system A and B, the conditional entropy will not change.
Okay, sir. Okay, thank you, sir.
But I think this is the only one. I don't think there is any other operation that it will remain invariant under. Yeah.
Thank you, sir.
Okay, so Gilad, thanks a lot. Very profound talk. It will give us a lot of material to think about. Truly appreciate your very well, delivered talk. Thanks a lot.
Thank you. Thank you very much.
Lakshman, are you around? So